screen because I stopped sharing. Good. I start now? Okay. Good afternoon, everyone, or good morning, wherever you are. We would like to welcome you to the midterm webinars, or the first midterm webinars of the Code for Earth program. And my name is Atina. I'm here with my colleague Esperanza, and we're supported by Sara Bozzi and Diego Domenici from Complat Trust IT. And without further ado, let's dive into what is Code for Earth. And then, today it's about the project teams, what they have been doing so far, where they are. It's midterm, so they are away from having final results, but we want to show what they are doing to a broader audience, to a broader community. And so it's their time. Before I move on, Sara, maybe you want to say a few things on the logistics.
Yes, hello everyone, I'm Sara, and just as a quick update on logistics, if you want to have, if you have some questions, if you need to ask something to our teams or to Atina or Esperanza or even us, just please write your questions on the Q&A section in the bottom bar of Zoom, and we will have a Q&A session at the end of the webinar, so you will be answered all of your questions at the end of the webinar. So sit tight, relax, and enjoy the talk from our panelists and from our teams, which are working very, very hard on their projects, and you'll get all your question answered at the end of the webinar. Thank you.
Good, thanks, Sara. Okay, so, oops, that was a bit too fast. Just some quick facts on Code for Earth. The program has been running since 2018, and it's a key innovation action run by the ECMWF. That's the European Center for Medium Range Weather Forecasts, and supported mainly by Copernicus and Destination Earth. And we have 2 more supporters, which I will show later. And the program welcomes each summer individuals or teams of developers. They was from different backgrounds in computer science or science and software development that work on predefined challenges. We call them challenges at the beginning. And that's a great opportunity for everyone to work on real-world scenarios. And it's all about working together, learning, and it's about innovation. And of course, it's about open source development. The selected teams that at the end of the coding phase, which is end of August, complete their projects, they receive 5,000 euro stipend. So we have run, these are the different steps in Code for Earth. We had a call for participation earlier this year in March and April. And then we evaluated all the proposals, all the submissions we received for the challenges. And end of April, we announced the selected teams. And in May, we started the coding phase. And this year, we have selected 13 teams that work with the mentors on the projects. As mentioned, it's a collaborative development. So the teams work together. They have progress meetings with the mentors. And today we want to share, we want to give the teams visibility, and we want to share some first results. And the next midterm webinar will take place next week, Thursday. And that will feature a different group of teams. So this is where we are at the moment. And I would like to thank especially our supporters for the 2024 edition, which is IFAB, the International Foundation on Big Data and Artificial Intelligence for Human Development, based in Bologna in Italy. And we have also support and a joint challenge with the Helmholtz Zentrum Herion in Germany, outside of Hamburg. And at this point, I would like to hand over to Esperanza.
Hello, everyone. The Code for Earth initiative couldn't be possible if the role of the mentors. In this year, in this edition 2024, 40 mentors from ISMW and also external mentors are helping the teams during the coding phase to work on the projects. So the names are, you can see on the slide, these 14 mentors who are a fantastic role here. Next slide, please. Yes, and these are the project teams that we will showcase the progress today in the webinar #1 session. 6 teams are presenting today, and they are Tales of Drylands, which are formed by 5 members: Marina Caporlingua, Xenofon Karagiannis, George Beckas, Lucy Colley, and Medina Abbas. The second project that will release the progress so far is SunVizor. It's formed by Sergio, Castillo, Perez, John Alberto, Lopez, Hernandez, Irma, Riadigos, Sanchez, John Anders, Sapirine, Manrique, and Xavier Elbertin Robles. The third project who is presenting today is vAirify. This is composed by Tim Johnson, Sebastian Steinig, Ahai Meha, Mike Walker Rose, Max Nyamunda, Ben L. Jones, Luke Vincent, and Richard Strange. Another project is CAMS MB Charts. It's developing by Xenofon Karagiannis. The 6 teams who is presenting today is KGB-TruthGuiding. This is composed by Việt, Duxin, sorry about my pronunciation, Yutin Yang, Dao, Tan Mirth, and Pham Bu Hon An. MLBs is the last team who is presenting today, is formed for Yikui, Zhang, Till Foreman, Johannes Leonhardt, Mohammad Hagan, Sams Edim. But there's next slide, please. Yes, this is the webinar #2. Will happen next week on Thursday, 25th of July. The rest of the teams, they will be present and showcase their projects. There were Air Quality Urban View, formed by Eloy, Codina, Oscar Hernandez, Andrea Fenoy. CAMS Visualizer, formed by Hakan Deniz Kale, Jack Book, Arda Orak, and Elif Rana Arslan. The third project will be presented this week is Hydrogap AI, formed by Yannis Kontos, Konstantinos Platiridis, Diamantis Karax, Sanis, Charis Stapridis, Nikos Saufolius, and Konstantinos Perifanos. Project Poly is the next one, following this order, is formed by Clive Drowley, Caitlin Rice, Matthew Chapman, Nadia Skifa, Holly Tenser, Matt Cousin, and Thomas Goldring. XAI for weather forecast models is formed by Michael Akayan, Andre Jeversim, and Adrian Berlik. And the last but not least projects, a Code for Earth projects 2024 will present next week are CDS API request check by Irina Sukorbeski and Tom Calloway, and optimizing CDS API, formed by Audrey Coder and Katalin Ionut's album. Next slide, please. Yeah, and now we can hand over the teams who are presenting today. They are with us. We are welcome, all of them. And the first of these is Tales of Dry Lands. So the speaker is Marina. Marina, the floor is yours when you are up to.
Thank you. I share my screen. Just a moment. Okay. So good morning or good afternoon, everyone. Thank you for joining us today for this presentation. My name is Marina Caporlingua, and I'm thrilled to be here with my colleagues to present the progress of our project, Tale of Drylands, Chronicles of Drought. This project is about understanding the story that climate their pattern and their impact and drivers. We have decided to dedicate our effort to this topic because generally we can think that drought is just a natural part of our climate's variability, and historically there have always been periods of dryness. However, in recent years, we have observed a troubling increase in the frequency, intensity, and duration of droughts. Climate change is driving these trends, and future forecasts indicate that many regions worldwide will continue experiencing more severe drought conditions. The following image from the Copernicus Interactive Climate Atlas illustrates a clear trend towards drier lands over the years, signaling a shift in climate patterns. The impact of drought extends far beyond the lack of water. It threatens food security and public health, triggers displacement and migrations, and severely disrupt ecosystems, leading to biodiversity loss and habitat degradation. So understanding the dynamic and impacts of drought is crucial, not just for climate scientists, but for every one of us, as it affects all aspects of our lives from the economical, environmental, and social point of view. The European Centre for Medium-Range Weather Forecasts provide free access to its data to encourage diffusion and awareness about climate topics. But accessing and analyzing this data can involve a significant barrier to entry for non-experts, because acquiring and utilizing this data demands specific knowledge. For those new to this era, deciphering the specific terms and understanding where to find the data can be challenging. After, they can experiment the difficulties of tailoring the data to their specific needs. And a final major hurdle is dealing with the data file, which often come in unfamiliar formats, and learning how to handle these files and extract usable information requires additional technical skills. So the aim of our project is to serve as a bridge, filling the gap between the availability of drought data and their practical application. We aspire to be the compass that helps everyone orient themselves in the landscape of drought data, guiding everyone to effectively address their unique needs. To achieve this, we are developing user-friendly tools and comprehensive educational materials designed to simplify the complexities of drought data. These resources are tailored to help us to access, interpret, and apply the data effectively to each specific circumstances. So we want to reach out to the broadest audience as possible. That includes students, teachers, journalists, environmentalists, citizens, and in general, everyone with a basic knowledge of Python, programming language, and statistics. Taking into account the varied needs and expertise levels of our audience, we are preparing different learning paths. This path in varying complexity and suit different skill sets and learning objectives, ensuring that everyone from beginners and to advanced users can find value and advancement in their understanding. Each path is designed with adaptability in mind, providing guidance and support as users grow their skills. Our toolkit, designed to achieve this goal, is composed of the primary data source, that is the ERA5 dataset provided by the ACMWF, covering climate data from 1940 onwards. This comprehensive dataset is crucial for understanding long-term climate trends and patterns. We are developing a Jupyter book that serves as a theoretical and practical guide, and it covers the basics of climate data analysis with a focus on drought. It includes essential information on informatics setup and Python libraries needed, along with a series of links and resources to further explore each topic. The book also offers a detailed explanation of the 3 Jupyter notebooks that are the core of our toolkit. These are designed to guide users step by step through the process of data retrieving and exploration. The insights gained from our journey through drought data are as follows. For the first notebook, the ability to recognize and track drought events globally and historically. This involves understanding the spatial and temporal distribution of droughts, enabling a clear view of their prevalence and shifts over time. In our second book, we delved into methods for quantifying the severity and anomalies associated with drought events. This includes interpreting the indexes that measure the intensity of droughts, providing a concrete basis for comparison and study. The third notebook is dedicated to identify and exploring the primary drivers of drought conditions, with a specific attention on precipitation and temperature. Understanding this factor is crucial for interpreting drought patterns. We are striving to simplify the notebook's interface for a broader readability. So we are optimizing this interface by including only the essential code for data selection and results visualization, while all supporting functions are housed in separate Python files, so reducing clutter and complexity in the main notebooks. This separation allows users with a deeper interest in the technical aspects to explore the underlying code at their own pace, without overwhelming those primarily interested in the analytical insights. We are also integrating a series of interactive widgets within the notebooks, enabling users to customize their analysis by selecting different geographical areas, time periods, and time scales. And this flexibility allows each user, or we hope that can allow each user to tailor the data exploration to their specific needs and interests. Finally, we are preparing an in-depth analysis of drought events in Madagascar. This area is an exemplar case study due to its frequent and severe drought period. These droughts have profound impacts on the island's agricultural productivity and food security, making it a critical subject for analysis and intervention. All our contents will be completed by September 18th, but we have already made our final GitHub repository available for those who are interested to follow our progress. And any feedback is welcome, so feel free to contact us via GitHub with any questions, suggestions, or comments that can help us refine our tools and ensure they meet the needs of our diverse audience. Thank you all for your attention and interest. Special thanks to our mentors who support us through this adventure, and to the ACMWF for providing us this invaluable opportunity to collaborate. Thank you.
Thank you very much, Marina, and all the team of these Tales of Dry Lands, and all of the mentors if they are here. Thank you very much. Very well presentation. Now we hand over the next team who is here with us is SunVizor. So it's the presenters here. The speakers are Sergio Castillo Perez and in Irma Riadigos. So the floor is yours when you are ready. We are preparing to listen to you.
Yes, thank you, Athena. Hi, everyone. I'm Sergio, and I will be presenting today, together with Irma, our progress regarding SunVizor project. Johannes, John Alberto, and Xavi have also been working on it, as well as our mentors, Nube, Eddie, James, Julie, and Melanie, all of them from ICMWF. So I would like to thank them all. The presentation has two sections. First, a PowerPoint to introduce the project to all of you, and then a live demo showing our progress. So here in the next slide, basically we present the project description and motivation and objectives. SunVizor project consists of creating an interactive web application for end users to effectively visualize data related to the renewable energy sector, variables such as 2-meter temperature, dust, solar irradiation, solar photovoltaic power generation, cloud coverage, and some others that came from different sources, C3S and CAMS, basically. The data is expected to be visualized at different time scales: historical data, next day's data, and climatic projections. So having said that, in a nutshell, our motivation and objectives as a team within this project, it can be summarized as that we think collaborating on a project with ICMWF, which is the vanguard in weather forecast and climatology prospects globally, will be beneficial for us. Also, getting along with all the products and data in the ICWF catalog, as well improve as a team our skills in data visualization. And finally, providing the renewable energy sector with a new layer of value regarding weather data access and visualization is also challenging for us because we are working in the industry. So moving to the data sources, as you may know, ICMWF offers a wide range of atmospheric and climatic data with different formats that come from different sources and are available in their respective catalogs, the climate data store and the atmospheric data store. So in this way, users have access to a lot of information that is important for the renewable energy sector. For example, they can retrieve historical data or forecast data about atmospheric variables such as temperature, humidity, solar radiation, and so on. Users can also access to climatic predictions for other variables of interest, such as solar power photovoltaic generation or electricity demand, and also observations coming from CAMS, such as global horizontal clear sky radiation, dust, or air quality. So considering these different sources, we have a problem because all this data has its own format, its own distribution, and different temporal and spatial resolutions. So end users need a way to obtain this information in easily user-centric application. So in terms of SunVizor's tools and architecture, we have first downloaded a glimpse of the data from different sources and formats in a virtual machine provided by ICMWF. And there we have installed the GeoServer that enables us to connect and publish the geospatial data easily. And with that in place, we are able to generate animated maps for users to visualize the data with Leaflet, which is a JavaScript library used to build web mapping applications. So this step will enable users to interact with a map and visualize data from a pair of coordinates or from a point in the map and see some visuals about this point selection. So having said that, it's time for Irma to offer a live demo showing our progress regarding data visualization. So Irma, the floor is yours.
Okay, thank you, Sergio. Okay, can you see my screen?
Let me stop sharing first. Yeah.
Okay, perfect. Okay, so hello everyone. So from my side, I'm going to do a short demo of the visualizer that we have been preparing. But first, I have to mention that we are working in parallel on the data processing and the front end part. So regarding the second part, we are mainly working on the functionality and structure of the web app. So the examples I'm going to show you now are based on a dummy data sample. So don't panic if you see strange values in the plots. And then what we have here. So here in this web page, you can see the main view of our visualizer. We have a global map with two important elements. First, here on the bottom, you have a time range selector to indicate from which date you want to browse the data. And then here on the top right, we have the variables selector. But before that, and just as a way of illustration, we have placed here on the top left this temporary selector, which has the option to choose between these two variables. We have the temperature and we have the wind speed, which are the variables that you are seeing right now over the global map. I'm going to select the temperature. Okay, so these are real variables downloaded from one of the data sets, vAirify, and they are coming directly from the GS server that Sergio was commenting. So they are just here as an example, but let's focus now on the main functionality of this application. Okay, so now let's imagine that I enter here and that I want to browse the data for a specific location. Let's say, for example, Spain. If I click here on the map, I will get this pop-up saying that first I must select at least one variable on the selector. Okay, so I go here to the selector on the right, and I choose, for example, the first four variables. Now I go back to the map and I choose my point. Now you can see the icon here, and if I click now, I will get this small box with some information about the average values of these variables that I have selected. So now I can click on show charts, and I will have the plots of all these four variables for the time range selected. You can see here the plots of the four variables. And here on the left, I also have the option to remove or add the variables I have selected. And then the most important part is that I can choose here the type of aggregation for the data. The default value is daily, but if I select, let's say, yearly, I will be seeing only the average values for the years that I have available. For this demo, we have only 4 years of data, so we are seeing only 4 points on this chart. I can also select monthly aggregation, and in this case, we are seeing the monthly means for the 4 years. And if I select hourly, I will see the data in an hourly resolution for the whole range of data. Okay, so this is the first approach for our visualizer. We still have a number of things to implement and improve. For example, we want to add more options here in the type of aggregations, and for the moment, these plots simulate only data coming from reanalysis data sets such as vAirify for CAMS. But we are working also on the implementation of another selector to include here in these plots both climate projections and forecasts. And also we want to have the option to click in another point in the map to be able to compare plots from 2 different sites. And that's all from this demo. Thank you.
You finished. Many thanks. Oh, it is really, really nice. Do you see this visualization now? Because you have the remaining time to finish the coding phase. You have 1 month and a half. So very, very good, very good. We are very pleased, all of you. Thanks for letting us know, showcase this.
Thank you.
Yes, thanks, Sergio and Irma. Now the next team who is with us is, the name of the project is vAirify. I don't know how you pronounce that.
Yeah,
team.
we've gone with an unusual name, vAirify, sort of a play on
okay.
verifying the air. So yeah.
Okay, so yes, let me present all the speakers. Will be Tim Johnson, Seth Steinig, Mike Walker Rose, Max Nyamunda, and Luke Vincent. Hand over to you, please. Let us know.
Okay. So yes, good morning, good afternoon, everyone. So yeah, as you see, we're quite lucky to have quite a big team. We are mostly from a software consultancy called Scott Logic, based in the UK, and we're joined by Seb, who's a climate scientist from the University of Bristol. And you can see there we're supported by 3 mentors, Mark, Miha, and Johannes. So first of all, what's our goal? Our goal is to develop an online dashboard for displaying and monitoring air quality forecasts for cities around the world. So there's an example air quality forecast in this map below. This is one from CNN, who do, as part of their normal broadcast, they will show what the air pollution forecast is for various cities. And this data comes from the Copernicus Atmosphere Monitoring Service, or CAMS for short. But how can we verify whether these forecasts are accurate? Well, we need air pollution sensors for those. The sensors look like these. There's 2 different types or grades, if you like. There's official, highly calibrated sensors that are shown on the top left there. But then more recently, there are low-cost sensors available. There's a whole variety of different shapes. There's one that's shown there. And these all plug into open data networks, OpenAQ being an example. So we've got both of those in there, and the addition of the low-cost sensors gives greater coverage. But we don't know how reliable or accurate those sensors are, and whether we can use that data for improving forecasts, and can we use it for spotting differences more quickly. So I'm now going to hand over to Seb to talk about the data.
Okay, thank you. We wanted to start with a brief overview about the kind of data that we use in this project. So we are using an aggregator called OpenAQ, which provides open access from a long list of different sources of open source air quality data. And in this map, I just showed you a typical return that we get for a query for our 153 cities that we want to validate within this project. So we are asking for any type of measurements within a 25-kilometer search radius around the defined city center for a list of 5 different pollutants, so particulate matter, ozone, nitrogen oxide, and sulfur dioxide. And in this case, I just asked for 1 week of data. And on the map, you can see the return that we get from this request. We get overall roughly like 600,000 measurements back distributed over 1,300 cities. And just by using this one source, we are already covering more than 100 of our target cities. On the next slide, I want to show you a very quick overview about the kinds of challenges that we have to deal with this data that we get returned. So I'm just showing 2 time series, one of ozone for Vienna and one for PM2.5 for Jakarta. So it's 1 week of data shown different colors there for different measurement stations for those cities. And you can see already just by IDA all sorts of different problems. There are gaps in the data, some potential outliers, some zeros returned. So what we did initially is quite a lot of work on screening the quality of the input data and putting it in a format that we can further process. And how we digest this data and integrate it into our system architecture is what Luke will show you on the next slide.
Thanks, Seb. So this is an image of the architecture. Diagram shows the data flow through the system. Starting at the bottom, we have 2 scripts to extract data from CAMS and OpenAQ. These scripts also transform the data so that the data from the 2 sources are comparable. As Seb mentioned previously. The transformed data then gets stored in the database. Having the data stored removes the need for refetching any data from the sources, allowing faster loading. And finally, at the very top, we have our web app dashboard, which pulls into the vAirify API to fetch data from the database. Next slide. So these are Python for the backend scripts, and the API is also in Python using fast API library. Using Python allows us to kind of use pandas and other data processing packages. And the UI is developed in React. What does the dashboard actually look like? So we have 2 pages. The first is a summary page. This is how it currently looks. On here, we're trying to show how accurate the forecast is for the various cities versus the in-situ measurements. The more poorly performing city forecasts are ordered at the top of the table. It's ordered by the difference in the AQI forecast. And we've also got the 5 pollutants relevant listed, which are ozone, sulfur dioxide, nitrogen dioxide, and the PM2.5 and PM10. We can then click on through to each city to see exactly how they are doing with a series of time charts. So we've got 6 charts. The first shows the AQI value over the last few days against the measure value. And then there are charts for each pollutant. Each chart shows all the measurement stations available from OpenAQ for that city. So we have various numbers of lines, as well as the dark dash line for the forecast. I'll pass on to Mike. Talk about how we're testing.
Hi, everyone. vAirify is being tested in the context of our agile development process. So our work is split into small pieces of functionality around requirements. We get something small working, we improve on it and get feedback and try and test as we go rather than at the end. Anything that has to always work or never happen gets put into a test case. For everything else, we're using targeted exploratory testing. So that's using test charters to try and find deeper bugs, essentially, because we don't know what the deeper problems are upfront. We're utilizing the testing pyramid. So we've got more tests lower down because they're cheaper and faster in terms of feedback. So that's lots of unit tests where we mock everything outside of the functions themselves. Integration testing, we're mocking everything except the integration point, and end-to-end tests with which we're going to have, which will have no mocking whatsoever and touch every layer of the application. How do we know that something that's tested now and works isn't broken later? We're trying to automate these regression tests where possible. So for example, in the back end, with Python's PyTest library, we've got test suites that cover in the integration section, the in situ and forecast ETL processes. So that's checking the data integrity all the way through, calibration with existing ECMWF, CNN forecast reporting, and all of the API endpoints. I'll hand over to Max.
Thank you, Mike. Good afternoon. So I'll be talking about Playwright, which is an automation library we've used for our kind of front-end UI and E2E testing. If you're familiar with Selenium or Cypress, it's quite similar to that. So this allows us to kind of test multiple scenarios across Firefox, Chrome, and Safari, which were the main kind of browsers that other mentors use and asked for. So this allows us to automate all the lengthy manual tests that have to be executed whenever we have like kind of changes coming in constantly. So yeah, some of the manual tests end up becoming quite monotonous with like so many changes coming through. So this allows us to automate things that should always happen, so we can focus on the exploratory testing, which is where all the bugs usually come out. Additionally, Playwright allows us to kind of mock our data so that we know that we'll get the same response back from the API every time. And in turn, this allows us to kind of assert on visual data, because that was kind of a difficulty we had in trying to understand how do we make sure that the actual data on the graph is displayed correctly. And that's where you see those kind of 2 graphs on the side there. I've been able to kind of create a kind of golden standard image, which is what we expect the graph to look like. And then Playwright will kind of run through a test, take a screenshot at the end, and it will show you the actual. So this one should fail, and it will tell you by how many pixels it's different by. Yeah, which is quite nice. So back to Tim.
Okay, so we've now got an air quality dashboard in place on a live server, and it's already being used. So for these remaining weeks, we want to continue to refine what we've got, make sure that it can be easily supported once the challenge has come to an end. But there's a lot more that can be done. So we've listed some things here, and we'd like to work against those. So for example, adding a map view, so that when you're looking for a particular city, you can see where the sensors are to see whether any are in unusual places and should be discounted. So yes, there's plenty to keep us busy. And just wanted to end with an example of what we've seen in the data. This is something we saw not too long ago. So this is a huge spike in particulate pollution, and we saw this on the 5th of July, which, with the time difference, we think is basically down to the Independence Day fireworks. So I thought that was an interesting signal in the data. So yeah, please come and have a look. There's a link there to the sort of development application, and there's the GitHub link as well. Please reach out with any questions.
Thank you very much, vAirify team. Very impressive. Thank you. And if you have the audience have some questions, we can deal with them at the end of the webinar. Thanks again. Now the next team who is with us is CAMS MV charts. It is working on by Akis Karagiannis. The floor is yours, Akis, when you are ready.
Hello. Screen. Here's my screen.
It's loading, yes, now.
Right. Yeah, so we baptized the project CAMS MB format, MB from notebook. The title is Prepared Notebooks for CAMS websites. I think this is the only solo project. So I'm working on it, and I have 4 people supporting this project: Nyamunda, Marina, and Chris, who are also in the SMWF. Now, CAMS means Copernicus Atmosphere Monitoring Service, and if you Google it, if you Google CAMS charts, you probably end up in this page where you essentially can view the forecast for different things like you can see aerosol focus or carbon dioxide or fire detection and stuff like that. And the idea is that instead of going there selecting to view the focus line, we have a way to reproduce all these forecasts programmatically. So this project that comes in the SARS project aims to do just that, access the data through the ADS, the atmosphere data store, and plot all those charts. Part of this is to use a Python package that has already started, development a few months ago, although it's still in a beta stage, I think. That's called FKit. There are several sub-packages: FKit data, FKit maps, and currently we use FKit maps to do at least the plotting of that. And the idea is to give the capability to different kinds of users to generate these charts. It might be for high quality prints and publications. It might be for training purposes, but within Jupyter Notebooks, right? The main challenge so far has been to bring everything under one roof, because it makes sense that there's much legacy code. So there's magics, and people like Milana and Mark, in the initial chats we had, were like, oh, I have this code base, my own code base to do this. So there isn't a single code base that people use to generate this so far. So the effort we have been attempting is to collect these bits and pieces to, to have a single point, a single repo that we can use to reproduce these charts. As I said, part of this is, the integration with the active packets. So, the ambition for this project is, in the end, to be integrated to that as a sub-module, a sub-package. Now, the generation of these charts means that we have to have a shared point where we have some mappings. Like when you want to plot a chart, you need to have some parameters for that, like which color scale to use, which levels in that scale, what's the conversion factor, or the units of measurements that you want to plot. So we've been collecting these in a single, let's say, configuration file, and the user that's on the part of that is on the left. You can see, for example, for plotting the focus for the horizontal optical depth, you have some parameters there, and the user on the right will pass a certain parameters similar to what they do online. Like they select the date they want to focus and the leading time. And once you do this, you end up with something like that, right? And part of this project, which I haven't started yet, is to verify that what we plot here is actually the same as the web page. And so, for example, like this, this I think was for 2 days ago with a leading time of 12 hours. So, you go to the web page, which is on the left here, and, you compare with the one that we generate programmatically on the right. And right now we have, a few of these sets working. We're collecting the rest of the parameters for other sets. But for example, you pass the total column of alternate parameters for the code to chart to plot, and you get that, or across particular matters. And yeah, we have like 8, 9, 10 focus that we can plot, and we'll add more into that.
Thank you very much. Thank you very much, Sakis. As we said, the question and answers, the people are ask questions something to your project. They will ask later when we finish the presentation. Thank you very much for your involvement. So next one with us is the project name KGB-TruthGuiding. So the speaker is Việt. Việt, if you are ready, the floor is yours.
Hello, do you hear me?
Yes, we can hear you.
Okay, yeah, perfect. So do you see the screen, the presentation? Okay, perfect. Yes. Thanks. So today I would like to present to you our project, which is KGB knowledge graph for better visualization of LLM answer. So for the agenda, first I would describe the problem description and solution for the problem, and next is our approach. And for the fourth, I would present a little demo, and for the final, I would like to show some future direction that what we can implement in the last month. So the problem description is that, okay, given a large scientific literature from ICMWF, we would like to find a way to organize knowledge and make it more accessible to ICMWF chatbot, internal chatbot, so it can generate a better answer, and it can generate a knowledge graph that could aid for the user using ICMWF chatbot. So for the source of the text, one source of the text is on the side here. Is technically it is a scientific report. Okay, so solution for this problem is that we're gonna use knowledge graph. So knowledge graph is basically a kind of data structure. So basically it's a graph, but for the node and for the relationship between the node, there can be many relationships. For example, in this graph here, we have Da Vinci, and he's painted the Mona Lisa here, and he also can be point to the node person here. So you can see that here it have multiple type of relationship. It can be painted. It can be so this is a way to organize knowledge. So for how knowledge graph can help the internal chatbot, ICMWF internal chatbot. So it can help this chatbot to enhance the knowledge retrieval. It can index knowledge better, and finally it can help to generate a graph to enhance the comprehensibility of the answer. So for example, if someone asks for, like, for example, for this picture, if someone asks for like who is a painter of Mona Lisa, they can show that Da Vinci here is he's a painter of it have this relationship painted here, but it can also show some neighbor of the Da Vinci is a person, and other person can be interested in Da Vinci, for example. So it can, in a sense, it can enhance the comprehensibility of the answer returned by chatbot. Okay, so our approach contains two steps. The first one is knowledge extraction. The second is knowledge storage, and the third one is visual aid knowledge presentation. And we do this step sequentially. So the first step is knowledge extraction. So for the knowledge extraction, first we extract raw data. So for example, in the technical report, it can contain many redundant information such as footer and header. So in that sense, we have to remove this one because it's repeatedly appearing a lot of text and it doesn't bring a lot of information. So first you have to clean this one. Later we have to remove the table and figure data, because for example, the table and the figure can appear in the middle of the paragraph, and this would cut off the continuity of the paragraph, and to extract information from this one can be challenging. So to enhance the continuity of the text, we remove the table and the figure. And after we remove that one, we have to identify, okay, even we already remove it, we still have to extract the table and figure description, because it's still a part of the scientific text. And later we have to extract the abbreviation, because abbreviation can be entity. So for example, here we see in the knowledge graph here, it can be that Da Vinci have some colon alias name, and if it's happening in the text, it would be when we extract this one, if it's not be referenced in the abbreviation table, it could be hard to understand. So in a sense, we have to also extract the abbreviation. And next, when we have cleaned the data and we have the clean text, we're gonna use LLM, large language model, to extract information. So what we want to extract here, so we want to extract the text, which want to extract information from the text. So for example, if we have a sentence like ACMWF is a organization which do forecasting, which do weather forecasting in midterm, the way we extract information from that is that we take this sentence, we put it in the text chunk extraction, we put a text chunk, and we extract information appear in that sentence. So first, we extract ACMWF as an entity, and it can other relationship is an organization. It is an organization, and it can do weather forecasting. So from this one sentence, yeah, LLM first is gonna add the text chunk to the database, and next they're gonna add the entity and the relationship appear in the sentence, and later the relationship between the entity and the text chunk is that the entity appear in the text chunk. So to enhance the answer returned by the LLM, when LLM extract information from the text chunk, we're gonna add this self-verify the answer, so that it wanna retrieve it's gonna avoid hallucination and return a better answer. So for the storage of all the knowledge we have extracted, we use Neo4j because it's a very because this is like a standard of in the knowledge graph extraction. And at the moment we are using a cloud solution. So for the workflow of the how to retrieve information from the database. So first, so at the moment we have the database. So when a user asks a question, it's gonna have a retriever here. The retriever gonna look into the database, which is a knowledge graph, and the retriever look in the database, and it's gonna look for the text which is similar to the question. And in this text, it contains some kind of entities, and this entity can and we're gonna return all of the entity and the text to the retriever. So for all the information we retrieve, we send it to an LLM, and the LLM gonna use all the text chunk retrieve and also node retrieve here, and it's gonna generate the answer and also generate the knowledge graph. So we're gonna prepare a short demo for our product. I will share my screen again. So here we prepare a short website for the chatbot. So basically, if we want to ask a question, what is an ICMWF model, is gonna return the answer and return the knowledge graph here. So as we can see from the knowledge graph here, for the color red is a primary context. So it is gonna return the sentence that is similar to the question, and this sentence contains certain note in here, right? And but there are certain note which is special, which is appear in every sentence. For example, here is ICMWF, and this note can point to, so it's because it's note appear in every sentence retrieve, so it should be special, and it should be important. So this can point to other text, and here is other text that contain the ICMWF, node here, and this node can also help to enhance the answer of the ICMWF. So after that, we put every sentence, the first sentence, the primary sentence retrieved from the which is similar to the question, and we also put in other node, other text which appear, we contain the important node here, and we put it all of it into the LLM as a context, and the large language model can use all the context to generate a better answer, and it can provide also small knowledge graph for enhance the comprehensibility. So here I share screen for the sorry, yep. So this is what we have at the moment, and for the future direction, we hope to better enhance the entity information extraction by using AI agent, and also instead of using large language model, we hope to use some classical model which is faster. Maybe the performance may be the same or better, and we hope to use a local database because we need to scale to a lot of technical report provided by ICMWF. So it is the end of our presentation. Thank you for your attention, and if you have any question, I would like to address that.
Thank you very much, Riad. Thank you very much for your presentation, for the good work of your team. Very well. Now I will have the last thing for today is MLBs, and the presenter will be Johannes Leonhardt. So the floor is yours when you are ready. So ask what you have done so far.
Yes, thank you very much. I would be very happy to be presenting this MLBs project, which consists of Till, Hakam, Yikui, and myself. And in this project, we're dealing with the machine learning-based emulation of land surface models. Land surface models, in a nutshell, what they do is that they model the evolution of some land surface variables, such as soil moisture or soil temperature, as you can see, for instance, in these plots on the right. So in the top, you can see modeled soil temperature at one specific point in time over Europe. And then on the bottom, for instance, you can see a modeled time series of soil moisture at one specific point in space. And this is basically what these models can provide. And this information is, of course, very valuable when used as standalone, for instance, for flood and drought prediction. But it's also used basically in conjunction with other models, for instance, for weather forecasting as well. So how these models work is basically by relying on sets of partial differential equations, which model basically these physical feedback processes between energy, water, and carbon fluxes. And this sort of brings me also to the problem with these land surface models, and that is that they are quite bulky. So for instance, on the right, you can see an overview plot of EC Land, which is the land surface model in operational use at ECMWF. And you can maybe imagine, as you see all these different modules and components of this model, that these land surface models are quite computationally expensive to run. And this is why at ECMWF, there was recently a first prototype being developed called AI Land, which is a machine learning-based emulator, which basically aims to emulate, so imitate what the model is doing, but doing so much faster by trading off maybe a little bit of accuracy that we would get with the original model. So this AI Land emulator is sort of the starting point for our project, MLBs, where we try, on the one hand, to improve AI Land, for instance, by unifying the data processing pipeline, by trying out different machine learning methods to do the actual prediction, by incorporating observational data sets also, and to by constraining the emulator to produce outputs which are actually physically consistent. And this, of course, goes hand in hand with the evaluation of this ALAND emulator, where we want to check the trade-off between accuracy and inference speed, analyze the spatial and temporal error variability of this emulator, and also check for agreement with observational data sets or physical consistency constraints. So this is a basic overview of what's going on in AI land. So in the middle, we have the actual model, which for the moment being could be any machine learning model. It takes as an input some model state, it's one specific time, and then also some auxiliary information. This can be static information like the topology of the land or land cover, or dynamic information like modeled weather variables or vegetation-related variables like the leaf area index. And then also we add some additional inputs like encodings for the location and also the time within the year, for instance. And well, this model, after taking all this as an input, basically predicts a state increment for the model. So basically how the state variables change from one point to the next. And it also produces as an output some diagnostic variables, which are not directly included in the model state, but they're still interesting for us in terms of these land surface models. So looking a bit closer at specific machine learning methods that we tried, basically, one method that we tried is XGBoost, which is a more traditional method using like decision trees, but training them more or less in a smart manner. And we chose this method because it has actually previously performed really well on similar tasks, such as climate model emulation or also weather prediction. And then next, we have a multi-layer perceptron, which is basically a simple neural network, the architecture of which is based on the AI land prototype implementation. And then lastly, we have a graph neural network, which is special in the, or which is basically different from the others, because it also allows for modeling neighborhoods between grid cells. So the other models run basically per grid cell, whereas this graph neural network contains some information about the neighbors as well. So going a little more into detail here, actually. So what we need to do to run these graph neural networks is first to construct a graph, which we do by just, for instance, choosing the k nearest neighbors of each grid point. And then basically the machine learning model operates directly on this graph. And here actually many different implementations exist. And we have tried a bunch. And the best performing until now is this UniMP, which basically, if you're familiar also with deep learning, basically uses transformer-inspired versions of graph convolutions. So we have basically implemented all these methods already, and we can show you some preliminary results here. So to basically evaluate the different models, we compute the, among other variables, evaluation metrics, the anomaly coefficient, correlation coefficient on some holdout testing period. And of course, this is preliminary because there's of course still the scope for all these models to be fine-tuned and improved further. But some interesting things that we find already is that XGBoost actually performs the best for most variables, especially the diagnostic ones, but also that UniMP, so this graph neural network implementation, performs better than the multi-layer perceptron for all variables. And so this is the first indication that this incorporation of neighborhood information is actually valuable. Then we also noticed that the quality of emulation is vastly different for different variables. Like for instance, here discharge seems to be a very hard variable to for the emulator to sort of reproduce. And then, of course, we also look at the inference times. So since we want these models to run significantly faster than these models, this is also an important component. And here we notice that the multi-layer perceptron is about 1 order magnitude magnitude faster than the other models, where you can sort of see the trade-off between accuracy and inference speed as well. So then we also can look at things like the spatial error variability. So here we plot the anomaly correlation coefficient across Europe for one specific variable, in this case, soil moisture. And what we can see here, for instance, is that the models tend to struggle in Scandinavia and also alpine regions, which may have to do with the snow cover, which may somehow mess with the emulator. And then what we also notice, and which effect which we are currently still investigating, is that this graph neural network seems to fail in regions with high lake covers. So as you can see here, over time, this error actually also accumulates. So at the end of the testing period, we get like nonsensical results here. And as I said, we're still currently not sure why this is happening and still investigating. So regarding the next steps of this project for the second phase of the coding, we want to, of course, incorporate observational data sets into the evaluation. So here, for instance, you can see on the right that we already found that ECLAD has somewhat of a good agreement with SMAP, which is a satellite for monitoring soil moisture. And we also think about including, for instance, MODIS information, which has products about leaf area index, land cover, surface temperature, and snow cover. And of course, there are many other data sets we could think about using. And secondly, we of course want to assess and improve the physical consistency of AI land. So here, for instance, we could check the energy balance and the water balance, among other effects. So with this, I'd like to thank you for sticking around for the last talk. And of course, we're happy to take on any questions you might have.
Thank you very much, Johannes. Very well done, you and the rest of your team. But as you say, there's half of the coding phases is still there, so you all have time to improve your projects, of course. And can we start the question and answers phase part?
Yes, so that has been an impressive insight into the projects, and as Esperanza pointed out, we are not through all. We have not reached the end of the coding phase. So we have 2 questions. So Jörn has a question for Irma. And that's a SunVizor project on the solar energy dashboard. Irma, is there a color or length scale for the preview variables?
Yeah, sure. Yeah, I mean, the color length scale can be added, of course, with no problem. But as we mentioned in the presentation, this preview selector is temporal because we still don't know if we want to include this option in the previsualizer or not. So we didn't include these options yet, but of course, they should be added.
Okay, thanks. There is another question. And I guess that's a question for Johannes. The last presenter, Nidhi Gopal, asked, what are the other methods of eliminating errors of spatial data analysis?
Yes, so if I understand correctly, it's about this large variation in terms of spatial, the variability of errors in space. So some things we're trying out to improve upon this situation, I guess, is to, on the one hand, as I said, use graph neural networks because they can also include methods, include information from neighboring grid cells, which may help for grid cells which are maybe hard to predict, but neighboring grid cells maybe are well predicted. And then another thing we actually also implemented is to include spatial, so information on the location into the analysis. And both of these were basically attempts at reducing this variability, but of course we cannot eliminate it completely. And I hope this answers your question.
Okay, thanks, Johannes. I have another question here from the one panelist to another. Is a question again for Irma and Sergio. Could you give us some insights on the data handling process?
Yeah, we are working on extract, transform, and load tools to transform data from the European Center catalog to files with a global grid to lat-long files. So maybe we can connect later to explain that process to her.
Okay.
Yes. I think someone, Mashiyatronak, has asked for the link of the tool. I think the tool is from your projects, yeah, Sergio and Irma. It was in the Q&A webinar chat.
Okay. Yeah, we have the code on GitHub, but it's not published yet. But we will do it. We will do it.
Mm-hmm.
So we can share the link.
Or maybe also when you finish your coding phase, you want to show publicly when everything is ready and you know, soon, I guess.
Okay, I see that we're not doing a good moderation thing, so the questions pops up in the chat, but that's fine, I think. Massimiliano asked if do you have a reference? Do you have some references about the unimped model you used by PYG? Was it included with the framework, or did you have to implement it from scratch?
Yes, I can also comment on this. So this is actually implemented in the PyTorch library, and the reference is it's Shi et al. From 2021. So UniMP for Unified Message Passing. I think you would find it if you search for it, for instance, on Google Scholar.
Okay, then there was a question if the slides will be made available. So we recorded the session, and this session will be, you know, the recording will be put on our YouTube channel. There is a Code for Earth YouTube channel. Give us a little bit of time to do it, but you will find everything there. And that said, if you have, you know, we will inform, you know, we will share the notes. We will share this as soon as it's on YouTube. We will share the link and we will communicate this with the community. So if you have not registered or subscribed to the newsletter, that is a very good opportunity to do so, or follow us on LinkedIn and Twitter.
Yes, I guess the recordings will be after the second session next week. So not before that.
Very good point. So I don't see any other questions. Yeah, that brings us to the last point. The step 4 in the process. So a big thank you again for all the presenters and the teams for the excellent job so far. You still have a couple of weeks to go. And then in September, 18th of September, and please mark your calendars, that's mainly for the general audience, we have the final day event that will take place in Reading. But for the broader community, you can join us online because this is a hybrid event. And here you have some more information. And Esperanza, I'm looking at you. Did we miss anything?
The only thing missing is that you need to stay tuned for the next week.
Yes.
Because the second session of these Code for Earth midterm webinars will happen on Thursday, to the 25th of July, next Thursday. So the 7 team, the 7 teams that remaining will showcase the progress so far. So please, we are looking forward to seeing you there. And also, you need to register on the website if you want to be an attendee to join the webinar. Yes, you will receive the link.
You will see it on our website.
Mm-hmm.
Good. With that, I would like to thank the organizing team, Diego and Sara and Speranza, of course. The audience, thank you for joining us, and mainly and most importantly, the presenters, you have done a fantastic job, and hope to see everyone tomorrow in a week.
Yes.
Thanks a lot for joining, and have a fantastic rest of the day.
Very
Thanks
well
a lot,
done.
everyone.
Bye.
Good job.
Good
Bye
job.
bye.
Bye.
Thank you.
Bye bye.
Bye.